Hi everybody. In this lesson, the goal is going to be to derive an expression for the electric field that surrounds a charged line. I'm going to walk through the derivation for the electric field, and I will probably split this video into several parts so that each part is shorter. It's very important that you take good notes as you watch this. You are going to be expected to basically do these types of steps. I'm going to show you how to use calculus to derive the electric field, and so this is one of the key things that you have to do in this course. All right, so on this cover page here, it gives kind of a picture of our general goal, and like we said, we want to find the electric field a certain distance away from a charged line. So this might be a wire of some sort, and it could have charges kind of smeared onto it. We're going to assume that the charges are evenly distributed. So we're going to make the assumption that this is a uniform distribution. I'll put that here. And we're going to be talking about lambda to describe that distribution. And if you remember, lambda is a constant, and it's measured in units of coulombs per meter. And so we're going to assume that the lambda stays constant as you go along the line. Now, the electric field, you could probably guess that the electric field points away from the line, just from your knowledge of electricity. And we are going to show that the electric field points perpendicularly away from the line. That's an important component of this. The vertical parts of the electric field will cancel, and we'll make that clear in just a moment. Okay, so we want to get a function here. Our goal is going to be to get a function where E is a function of the distance away from this line of charge. Okay, so I'm going to flip to our next picture here, which is a diagram that we're going to use for the derivation. And I know you guys have this in your handout. And so the goal, again, is to derive the expression for the net electric field at a point P along a line which bisects a uniformly charged line segment of length 2a and charge density lambda. Then we're going to extend our results to find the field at a point outside an infinite line of charge. So I want to stress that right now, that when we do this derivation, we're going to just basically consider a line segment here. So we're not starting with an infinitely long line. We want to start with a line which has a limited length. And so we're going to make the total length of that line equal to 2a. So the top half is a, the bottom half is a, and that total length is going to be 2a. Let me say a couple of other things. I want to talk about this picture. This picture is very important. Okay, so let's talk about all the variables that are in here. One thing you're going to notice, first of all, is the point P. That's the point of interest. Okay, that's where we want to find the field. I hope you recognize that x is in here. X is the distance from the line segment perpendicularly out to P. All right, so this is a perpendicular distance, and x is basically the line. It's like the bisector that bisects that segment, and then x comes all the way out. So x is some position here where P is. We talked about how A would be the length of the top half, and A is the length of the bottom half. And now let's start talking about electric field. Okay, so here's where we start to think about calculus a little bit. In order to figure out the field, we are going to divide this line up into small pieces called dq's. And this dq up here is we're going to treat it like a point charge. That's a very important assumption, that we're going to make, because this is calculus small, right, this dq, that we're going to assume that that can be treated as a point charge. And so we're going to basically calculate the electric field from a point charge, and how strong would that field be over here as it points away from that point charge. So this is very much like problems that we've done in the last week and a half. So this is just a charge, that's a source. Here's your point, this would be the electric field. And the electric field continues along this line that connects the two things. Okay. Now, the calculus end of this is going to come in from basically letting dq start up at the top and move all the way down to the bottom, and we're going to add up all the electric field components from that. And so we're going to need this variable y. The variable y is a variable. It can range from plus a at the top all the way down to minus a at the bottom. And so that's going to be a variable that we're going to need to use in the derivation. Other things that show up here, the angle theta. This angle also changes because as you move dq up and down this line, you can tell that theta is also going to change. Theta could be big, it could be 0, it could be negative, but it's going to go up and down. That theta is the opposite in interior angle here. This is also going to be the angle that the electric field vector makes on the other side. And I hope you can agree that the electric field points away, and I hope you can agree that this theta is equal to that theta. They're opposite interior angles. Okay. The last thing I'll point out here is going to be that the electric field vector has components. Okay. And I remind you that the electric field vector here is really just a little piece of the entire field. This is not the answer. So this is dE, and that means that it's just basically a calculus small, or a calculus component of the electric field. So this dE is coming from this dQ. And there are a lot more of these dEs that we're going to have to add up for every dQ. So this picture is just showing the contribution to the electric field from a single dQ in our picture. It's not showing everything. The picture also shows that dE has components. You could draw a rectangle around dE, and you could talk about its y component, and you could talk about its x component. So we're going to use the components when we find the net electric field. And so we need to recognize that this dE has x and y components to it. Okay. All right, let's set up one more thing here. So we've talked about our picture. That's good. Let's come back to the idea of lambda. We said that lambda is charge density. I'm now going to write an expression for it. I'm going to say that the entire line segment here has a total charge. So big Q is total charge. And let's say that the length of that is going to be equal to 2a, right? Because of our picture. So this would kind of be like our global charge density, okay? So this is kind of the global density. When I say global, I mean it's really just looking at the average of the entire line segment. What we're going to do in our derivation is make an assumption that that global density is also equal to the density on a very small microscopic scale. So we're going to assume that that Q over 2a is also going to be equal to the density that you would find if you looked on a very small, like a local scale, local or microscopic. So this would be kind of the local density. And I hope that makes sense to you. We've talked about this before for mass densities. But the overall average density here should be equal to the local density. And of course, both of those things are just equal to lambda, which is a constant in, which is some constant, which is measured in coulombs per meter. I'll put that up here. Okay, so we're going to use that for an important substitution. So at this point, I'm gonna stop the video here, and in the next video, we're going to actually do the calculus, and we're going to use the picture, and we're going to use these this substitution here. All right, we'll see you soon.